Hello, this is topic number 3, Computer Systems Engineering Technology, topic basically computer and networking concepts. This is for Course STM-101, Exploring STEM Technology Careers, the spring of 2026. So I'm going to shut off my talking ahead and we'll get started. So I'm going to start off talking about digital electronics technology. We call it the beginnings. And if you look back historically, one may trace the beginnings of the computer to the end of World War II, when the government funded many projects to build the first electronic computing devices. This was done in an effort to strengthen the military, actually to calculate firing tables. That is, how far a projectile would travel, for instance, shot out of some type of cannon or gun. And there's actually been several movies recently about this, who did all these firing tables before and so forth. These early machines used the technology of the day, relays and vacuum tubes to implement their operation. In fact, like today's evolving cellular generations, the vacuum tube-based computers were known as first-generation machines. Going back to the firing tables, actually, if you think about it, there were a lot of naval vessels, destroyers and so forth that had these large, huge guns on board, and they could launch projectiles 20 miles. So if you think about it, the elevation of the gun, where it was aimed relative to the horizon, where it was aimed relative to, east, west, north, and so forth, if the wind was blowing, how much the power of the charge was that launched the projectile, the weight of the projectile, all that stuff makes for a lot of difficult calculations to figure exactly where that warhead, if you will, the projectile will land. So again, it was a very daunting task at the time to do it just with people. So again, this was a big push to try to get some type of calculator or computer that would take and do this automatically. So these are early attempts to build computational machines or computers, use logic circuits to implement their calculating functions, the memory, and other aspects of their operation. Now, at that time, almost 100 years ago, the technology today really wasn't very fast, but it was a start. And at this point in time, digital technology and digital computers have transformed society in so many ways, that is, in our present time. Furthermore, with the advent of AI, artificial intelligence, and quantum computers, we are ready to take another society-altering step in our ability to use machines to aid humanity. At least we hope is to aid humanity. This is a picture of the first ENIAC. It was named at Penn State University in mid-1940s using vacuum tube technology. ENIAC was the acronym for Electronic Numerical Integrator and Calculator. And you can see all the jumper cables. The way you program this thing was actually by taking and wiring it to do certain operations. This thing used 18,000 vacuum tubes. People calculated that probably wouldn't operate more than about 8 minutes at a time before a vacuum tube would burn out. And it turns out that to fix that situation and actually take and burn in the vacuum tubes, that is, use them in some other application to make sure they didn't undergo failure when first turned on. Because reliability, people knew about what they called infant mortality. You first turn an electronic device on, it's prone to failure, then you have old age. In between infant and old age, there tends to be a constant mean time between failures, but again, if they didn't burn in the vacuum tubes, again, the calculations were this thing wouldn't keep running for long at all. Here's a IBM 701 computer from the early 1950s, and you can see the operator of this computer is shown at the computer's control panel. Note that data was able to be loaded directly into the computer via switch banks. Those are the lower rows on this panel right below his left hand. And there's a bunch of pilot lamps indicating the status of the CPU operations above his hand on the control panel. So transistor technology basically started in 1947 and was disruptive to vacuum tube technology, and this new technology's many advantages gave rise to the second generation computers. Those are computers based on discrete transistors. Integrated circuits, or ICs, were introduced in the 1960s, and it did not take long for them to be incorporated into the third generation of computers. ICs themselves underwent a long-lived evolution, with various monikers being used to indicate the scale of chip complexity. SSI, or small-scale integration, became MSI, medium-scale integration, became LSI, large-scale integration, became VLSI, very large-scale integration, became ULSI, or ultra-scale integration, and that became finally grand scale, or GSI, and so on. IC technology was great for computers, since computer processing power is based on repetitive circuitry, which was the easiest type of IC to design and implement in the day. Enter Moore's law, and the race was on. If one had a certain size memory chip, one could reliably predict when one would have a chip with 4 times the capacity. The design of logic circuits had undergone a similar evolution, with relay logic, vacuum tube logic, then diode logic, resistor-transistor logic, and then the long-lived TTL, or transistor-transistor logic. Here's a slide of Moore's law, predictions of 1 trillion transistors on a chip in the year 2030, which is only 4 years from now. You see the line on the chart starts about 1970 with the introduction of the first microcontrollers, microprocessors, and it's headed for 2030. That's 6 decades worth of Moore's law holding. Actually, Moore's law is nothing but an observation. And it says on the right of the slide, aspiring to 1 trillion transistors in 2030. And it's got some check marks there with a ribbon FET, power via high NI, which I'm not really sure of what that means. And then 2.5D and 3D packaging. So those are all technologies that people are now implementing to be able to put more transistors on a chip. Again, continuing with digital electronics technology, Moore's law has predicted what was on the horizon for over 6 decades now, and from the previous slide predicts ICs with 1 trillion transistors on them in 2030. Quite amazing. This unrelenting micro-miniaturization and advent of digital technology has changed electronics totally during the last, should be 60 years. Today, most everything we do with signal processing, multimedia, communications, and control systems is done in the digital domain, even though the world is analog and we are analog beings. So this presentation will cover information representation, basic logic circuitry, combinational logic circuits, which serve as larger building block components, and other digital electronics topics. Another presentation will cover more complex digital systems that we usually talk about as computer peripherals, like mass storage and displays and so forth. Again, today this type of technology is not very repairable, and we tend to just throw it away if it stops working. Then and now. One should be aware of the fact that although there is a great deal of digital electronics in the field based on logic circuitry, and it is still used in new designs where appropriate, today, using newer digital programmable technology, we can replace most of this older technology with an inexpensive but high-powered microcontroller. This is another consequence of Moore's law. The cost of hardware approaches 0. In other words, we can replace hardware with software. This idea should be in the back of our minds when we spend time looking at digital electronics. It is important to understand what digital logic devices can do, but it is also important to realize that their functions can now be implemented with a cheapo micro and some software. So the title of this slide is Information and Binary Number Systems. In a microprocessor / microcontroller, zeros and ones are typically represented by a physical parameter like a voltage or current, in a kind of on or off scenario. That is, on is a 1 is a 0. A 0 could be a low or negative voltage potential, while 1 could be a high or positive voltage potential, or vice versa. The binary number system, instead of our standard decimal number system, is used to represent mathematical values, that is, numbers. The binary number system, like our decimal number system, is a positional notation system and obeys the same rules. However, its utility for use by electronic computing devices is that there are only two symbols, 0 and 1. And therefore, this fits the two possible states, on and off, of the particular physical parameter being used to represent the state, again, 0 or 1. The next several slides will provide examples of the binary number system. The base 2 number system uses two symbols, 0 and 1, whereas the decimal or base 10 number system has 10 symbols, 0, 1, 2, 3, on and on to 8 and 9. Using binary or the base 2 number system, one can represent the numbers 23 or 107, those are examples here, in the base 10 or decimal system by the following 8 bits or 1 byte of binary data. So I show here in parentheses 0, 0, 0, 1, 0, 1, 1, 1, and I say that's a base 2 number, a binary number, is equal to 23 base 10. Our normal decimal notation. Down below that, I show 0, 1, 1, 0, 1, 0, 1, 1, a binary base 2 number system, is equal to 107, standard decimal and base 10. So how does that happen? Well, again, the decimal number system uses positional notation. Most of us learned this in elementary school, but we most likely were not aware of this type or the terminology that I'm using here. The decimal or base 10 number system has 10 digits, 0 through 9, that's a total of 10 digits, with the largest digit being one less than the base. So the decimal number, for instance, 564, consists of 5 hundreds, 6 tens, and 4 ones, or 564. Or, as I show in the last bullet here, we could represent 564 as 5 times 10 to the second power, plus 6 times 10 to the first power, plus 4 times 10 to the 0 power, which equals 564. So this representation of 564 shown here is what is meant by positional notation. So in the first position to the left of the decimal point, the base, in this case 10, is raised to the 0 power. The next position to the left, the base is raised to the first power. The next position to the second power, and so on. So as you see here, 5 times 10 to the second power is 5 times 100. 6 times 10 to the first power is 6 times 10 or 60. 4 times 10 to the 0 power, and this one you might guess is kind of mysterious. But to make mathematics work, mathematicians have all agreed that anything raised to the 0 power is equal to 1. So anytime I have x to the 0 power, I get 1. So 4 times 10 to the 0 power is 4 times 1, or 4. And again, that adds up to 564. If I had, say, 1,564, that would include to the left of this number 1 times 10 raised to the third power. And again, say we had 10,564, we'd have 1 times 10 raised to the fourth power, and so forth. So this is how positional number systems work. For a different number base, the same organization holds. Back in elementary school, you might have heard a teacher tell you something like, we're going to add things in the ones column, we're going to add things in the tens column, we're going to add things in the hundreds column. That's kind of how you learn about decimal arithmetic. So the binary number base, again, the binary number system also uses positional notation, but most likely you did not learn this in elementary school. Again, the binary base 2 number system has 2 digits, 0 and 1, with the largest digit being 1 less than the base. So the binary number 10111 is equivalent to 16 plus 4 plus 2 plus 1, or 23 decimal. And I show this worked out down below here. So the first one of 10111 is 1 times 2 raised to the fourth power, plus 0 times 2 raised to the third power, plus 1 times 2 raised to the second power, plus 1 times 2 raised to the first power, plus 1 times 2 raised to the 0 power, which equals 23. Now I do them out down below. 1 times 16 plus 0 times 8 plus 1 times 4 plus 1 times 2 plus, again, the last 1 times 2 raised to the 0 power is 1 times 1. That all equals to 23. So you can see how you can convert binary into decimal. Not as easy to convert decimal into binary, but there's ways to do it. So what about the binary number system in computers? Since the base 2 number system uses positional notation like the common decimal system, there are rules that govern the fundamental math operations like addition, subtraction, multiplication, and division, just like you learned in elementary school. Therefore, as it turns out, electronic circuitry can be built that will implement the needed steps to replicate these common math operations. This type of electronic circuitry is called or known as logic circuitry. Today, it's quite easy to build an electronic adder circuit that can add 2 binary numbers together. How about the representation of text? One might ask, how does a text editor like Microsoft Word store text files using binary? Because so far we've just seen binary to represent numbers. So through a selection of binary codes, any alphanumeric symbol can be encoded in terms of zeros and ones. Excuse me. ASCII code has been standardized for a representation of alphanumerics. That is, computer keyboards automatically convert a key strike into an ASCII character for input. ASCII, by the way, stands for American Standards Committee for Information Interchange. Each alphanumeric symbol can be encoded as a binary combination. So again, up above ASCII, the acronym is outlined there as American Standard Code for Information Interchange. So let's take a look at some examples. The lowercase letter A. If I look at my computer keyboard, I see a capital A, but I know unless I hit the shift key or the caps lock, what will happen is I type that key and I'll get a lowercase a. What will happen, the keyboard will convert that to a binary symbol that is shown here as 0110001. On the other hand, if I do hit the shift key or the caps lock and I hit that button on my keypad, capital A is represented by the following binary combination. It looks very similar to this letter, the small a, but capital A is 01000001. So again, I've used 8 binary bits to represent either lowercase a or capital A. ASCII code is also used to encode punctuation and non-printable characters like, say, the carriage return or enter key on a keyboard or escape, ESC. All the functions characters on a keyboard, all the F1, F2, F3 on the top row of the keyboard, anything that like a question mark, quotation marks, parentheses, all those things are representative or can be represented by an ASCII code, a binary code. What about hexadecimal code? Other codes are also used. Hexadecimal coding is used as a shorthand notation to reduce confusion when communicating a long string of zeros and ones. So hexadecimal uses 12 symbols, 0 through 9 and A through F. For instance, for the previous ASCII examples, lowercase a, which is equal to that binary combination parentheses in the middle, that ASCII code is equal to 61 in hexadecimal. Now, how do you generate the 61? Well, if you take and go back to the middle 8 binary bits in parentheses, you take a look at the first 4 binary bits, you got 0110, which is 4 plus 2 or 6. So 0110 is equal to binary 6. The next 4 binary bits, 0001, are equal to 1. So 61 hexadecimal, I've broken each 4 binary bits into a hexadecimal code. Capital A, on the other hand, is going to be 41. And again, you go to the first 4 binary bits, you see 0100, that's 4, and then 0001, which is 1. Also, for the binary number examples we had before, say 23 in base 10 was given by the binary code in parentheses in the middle, If you take the first 4 bits, you see a 1, the next 4 bits, you see a 7. So that's 17 hex. And instead of saying 17, which you might be inclined to do, you want to say 17, because again, it's hex, not decimal. 107 in base 10 is given by the 8 binary bits in parentheses in the middle. If you take the first 4 bits of those 8, you see 6. The next 4 bits, 1011, which stands for hexadecimal B. So 107 decimal is 6B in hexadecimal. The reader may not be aware of the fact that the calculator that comes with the Windows operating system has a mode available in view mode called Programmer that can perform all these conversions. That is binary to decimal, decimal to binary, binary to hex, and so forth. One should give it a try or Google an online calculator capable of the same functionality. I don't believe in Windows 11 that the calculator is shown. I think you have to take and add it. Other representations of numbers. Other number representations also are possible. One of the most common being binary coded decimal, or BCD. There are 8-bit or a byte of information. Well, this is where an 8-bit byte of information represents 2 decimal characters. So I show an example in the middle bullet here. 0111 0011 base 2 is equal to 73 in BCD. How do we get that? Take the first 4 bits are 01111. I think I had an extra 1 there. 0111 is equal to 7. And then the next 4 binary bits, 0011, is equal to binary 3. So that base 2 number is actually 73 in binary coded decimal. The highest number of binary coded decimal we go up to is 9. So this type of coding was often used in early handheld calculators, digital multimeters, and what we call DMMs, and other electronic test equipment that use 7-segment displays. So this slide shows a BCD 7-segment circuit. The diagram shows the circuitry used by typical LED display of an instrument before the advent of inexpensive LCD displays used today. So if you take a look, here's a IC1, an integrated circuit powered by 5 volts. It's a 7446 was the numbering of it. It has 16 pins. On the right-hand side, we have a 7-segment LED display with A, B, C, D, E, F, and G as the segments. And then we have 7 resistors, R1 through R7. Those 7 resistors, 220 ohms apiece, are to keep the LEDs from drawing excessive current and burning out. So it turns out that I would put inputs into the 7446, and the bullet on the left shows the inputs of the 746 IC. A, B, C, and D would receive a 4-bit binary BCD value, which means it goes from 0 to 9, and the internal logic circuitry of the IC would provide the correct combination of voltage levels on the A to G segment lines to light up the correct number, and that correct number would have to be from 0 to 9. Other representations. Today, for computer networking, Internet Protocol version 4, or IPv4, uses a shorthand notation for IP addresses that is a combination of binary octets given in dotted decimal form. For example, a typical home router might have an IP address of 192.168.1.1, or the router might have an IP address of, say, 10.0.0.6. This first IP address above actually represents the binary value of, and notice I've written it out as 32 binary bits, 4 groups of 8 binary bits, or 32 bits. The first on the far left, the first group of 8, 1 1 followed by 6 zeros. Well, if you convert that to decimal, that's 128 plus 64, and 128 plus 64 is 192. The next 4 bits, the next 8 bits of binary, actually, if you figure it out, it'll be 168. And the far 2 8-bit groupings on the right are both 1s, 1 and 1. So that's the .11 in the 192.168.1.1. And again, why do we do this? Well, the shorthand notation, If I was to call you up and say, I'm going to give you an IP address, it's going to be 32 binary bits, you would try to hold me up and say, wait till I get a pencil and paper. And even if that was the case, you had a pencil and paper and I started rattling them off, we would be prone to making an error possibly. And you might ask me, have to repeat it over and over again. Whereas if I tell you it's 192.168.1.1, you can write that down and then convert it later on without too much difficulty. For IP version 4, the 32 bits are arranged as 4 binary octets, which are converted to decimal values. Hence, we call or use the term dotted decimal notation. Now, IP version 6, the successor to IP version 4, and why is this needed due to the exhaustion of IP version 4 addresses? You might think 32 bits, but you raise 2 to the 32 power and you discover that you don't have that many locations or IP addresses available to you. So IP version 6 uses hexadecimal shorthand notation to represent 128-bit IP version 6 addresses. That is, for the want of anything better, is a descriptor, what we call semicolon hexadecimal notation. So the 128 bits are arranged as 8 groups of 4 hexadecimal values. 4 hexadecimal values represent 16 binary bits, which are separated by semicolons. So here's an example. An IP version 6 address is 3FFE. Notice 1000. I don't say 1000, I say 1000. Semicolon 5000, semicolon AFFA, semicolon 2000, semicolon 4000, semicolon FFFE, semicolon 12AA. I try not to fall into the problem of using decimal numbers when I shouldn't be. That's a valid IP version 6 address. Now, you might be totally overwhelmed by that. 128 bits is a lot of bits, but it turns out that what happens is we restrict the use of various addresses in IP version 6, so it actually is a little more easier to use than what you might first think of here when you first see an IP version 6 address. So, information representation matures. As digital technology matured and its advantages became apparent, it was adopted by other applications to store audio, video images, or what we know today as multimedia information. Audio and video may be digitized, the images stored as digital files. Today, an image or high-definition HD video may be displayed on a screen as an assortment of pixels. The information for each pixel may be stored in multiple memory locations as codes for the color, brightness, and so forth. So let's summarize binary information. Let's conclude our discussion of codes by again stating that computers represent and store information as combinations of zeros and ones, not hex codes or dotted decimal. We use these for our own convenience. The computer knows whether a binary combination is an instruction, a number, an alphanumeric, or some type of multimedia through various built-in hardware system cues or through the software program. That is, consider that Microsoft Word uses the file extensions of .doc, .docx, etc. And today images are stored as .jpeg, .png, .tiff, etc. So those are the cues that tell us what type of information is being represented by the binary zeros and ones. A common thread during this discussion of information representation in binary number systems was that all our examples of descriptions of info used either 8 bits or a multiple of 8 binary bits, or what we call a byte of information. Typically, the basic computer word is some multiple of 8, since the basic memory size is also 8 bits or a byte. An ASCII code fits in a memory location. An IP version 4 address takes up 4 memory locations. IP version 6 takes up 16, and so forth. A computer will have a certain set of instructions that it can perform under program control. As we have stated already, these instructions will be represented by some binary combination of code or code of zeros and ones. Again, let us state that all information in a modern computer is represented by combinations of zeros and ones, numbers, alphanumerics, multimedia information, and instructions, which the computer can perform are all combinations of zeros and ones. Let's consider multimedia information in a little more detail. We may store signals, that is audio, video, and multimedia images, as zeros and ones in memory if we do this in an organized fashion, so that we may retrieve this info for future use. This fact also implies that we must transform these signals and/or images from the analog to the digital world. This transformation is typically performed using A to D converters, or ADCs, and D to A converters, or DACs, for signals and software for images. At this point, that technology is in a very mature state. Today, we're at the very beginning of the quantum computer era. These types of computers represent information differently than today's binary number-based machines. Quantum computers represent information using what we call qubits, or quantum bits. Quantum bits can store a 0 or a 1, but thanks to a concept called superposition, something that occurs at the atomic level in the quantum world, they can also contain 0 and 1 at the same time. It is essentially a form of multi-dimensional storage. So now we're going to shift gears and talk about logic circuitry, or logic gates. Logic circuitry was mentioned in the first slide of this presentation. What is it and how is it used? Logic circuitry is electronic circuitry that implements Boolean algebra. Boolean algebra is a branch of mathematics that deals with operations on logical values with binary variables. There are various laws and theorems of Boolean algebra, but we are most interested in the Boolean operators and, or, and not. These are binary operators. We refer to these operators as logic gates. So here's a nice pictorial diagram of logic gates. On the top we have the gate name, and then we have a little descriptor down below, the algebraic expression also. So we have a not, an and, an or, a NAND, NOR, exclusive or, exclusive NOR. The gate symbols, again, the third thing down, and then a truth table. So the not gate, the first one on the left, you put a 1 in, you get a 0 out. You put a 0 in, you get a 1 out. That's shown in the truth table. The next one, the AND gate, only if you put 2 1s into the input of the AND gate do you get an output. The OR gate, if you put a 1 on any input, or 2 1s, you'll get an output of 1. When you have 2 zeros going in, the output 0. The NAND gate is just the opposite of the AND. The NOR gate is the opposite of the OR. The exclusive OR, only when the 2 inputs going in are different do you get an output. And the exclusive NOR, only when the 2 inputs are the same do you get an output. You might question, why do we have all these different gates? Why not just the not, and, or? Well, it's because the technology that we use to implement these things gave rise to the NAND and NOR. TTL logic, when you design a TTL logic gate, the outputs were low compared to being high for the AND and OR gates. So it turned out TTL logic was a very popular integrated circuit, and NAND and NORs became the predominant gates. Exclusive ORs and exclusive NORs have a little bit different reason why they became popular, to do different logic operations. So, I think I've covered this on the prior slide. You can look over this again if you want. In the truth table, 1 stands for the logic proposition of true, and 0 stands for the logic proposition of false. Hence the term truth table. Where in the digital electronics world, 1 and 0s are electrical signals, typically high and low. One of the things you might question, what do we mean by high and low? In TTL logic, a 1 was 5 volts and a 0 was a 0. So, logic circuitry technology. Logic circuitry technology. As microelectronics technology has matured, logic circuitry has also changed, going from diode logic, or DL, to resistor-transistor logic, RTL, to the many families of transistor-transistor logic, DTL, to complementary metal oxide silicon, or CMOS logic, emitter-coupled logic, ECL, and other high-speed variations of these technologies. Again, I talked about this earlier. The TTL logic gave rise to the popularity of NAND and NOR gates because the technology of TTL made these gates easier to implement as integrated circuits. So now we shift gears again to take a look at combinational logic circuitry. Basic logic gates can be combined together, known as combinational logic, to create more complex subsystems like adders, counters, flip-flops, registers, multiplexers, demultiplexers, encoders, decoders, etc. These are all the building blocks of modern computers. So here's a block diagram. I have a combinational logic circuit, a bunch of logic gates inside that box there. Multiple inputs, say A, B, C, and D, and one or more outputs, X and Y in this case, coming out of that combinational logic circuit. So what these things look like in implementation, back many years ago, they gave rise to the 7400, which is a TTL series of logic gates, and combinational logic gate ICs, and the 4000, which is the CMOS series of logic gates and combinational logic gate ICs. So here you see a 7400, it's called a NAND gate, and it turns out it's a DIP chip, which we'll see in a second, and it had 4 NAND gates in there. A 7402 had 4 NOR gates inside of it. A 7404 had 6 inverters. Here's what these things look like. They were used in what's called through-hole logic, something we don't use anymore. Today we have what we have different than through-hole is surface mount technology. So again, that's what these things look like. We had a company across the street, Digital Equipment Corporation. If you went and visited them back in the 1980s and 90s, you could see barrels of these chips. And here's the 7400 series. Again, a little bit different. And again, you see the little picture down below, the through-hole technology. We would actually insert these things into printed circuit boards and solder them in there. So in theory, you could actually repair something. If one of these chips went, you'd actually remove it and put a new one in. So today, modern logic circuitry, I say here that through-hole era technology is way in the rear-view mirror. Today we use surface mount technology, and we've had several more decades of Moore's law. So today we have devices known as field programmable logic or gate arrays. We call those FPLAs or FPGAs, and very inexpensive, high-performance microcontrollers which have all but replaced our combinational logic gates of the past. We have gone from boards to systems on a chip, which the acronym is SoC. So here's field programmable logic arrays or gate arrays, and as it shows here in the slide, architecture consists of digital logic. You can make an ALU out of this, multipliers, you can make a DSP out of this, large-scale memory, lookup tables, built-in processors, parallel operation, massive 2D array of impressive order, extremely interconnected. So big FPGAs offer millions of gates, thousands of ALUs, integer floating point arithmetic, DSPs, which are digital signal processors, megabits of local memory, lookup tables, and multi-gigabit connectivity. And you can take and program this with a computer. So here's a Zertec. I'm not sure if it's an FPLA or an FPGA. And again, surface mount shown in the bottom right little picture there, where these things are mounted on the surface of a printed circuit board. And the pitch of those things, you see the big chip on the little picture there. There might be a space in one couple thousands of inches between the pins. Very difficult to take and remove a part like that off of a surface mount board. Here's a picture of a Arduino Giga R1 with Wi-Fi. So here's typical today. We have something like an Arduino microcontroller that can talk to other things over the air, and again, surface mount technology, as you can see. So if we do a digital technology summary, I could say, driven by Moore's law, we have made unbelievable strides in the micro-miniaturization of electronic devices. These improvements are expected to continue for the foreseeable future, and when and if Moore's law comes to an end, there are already other technologies being developed in the lab as we speak. In the next presentation, we'll examine the concepts of the operation of some of these digital subsystems that we have already mentioned in this presentation, and talk about today's digital technology and where it's headed. So You might want to take a look at this video. This is how a CPU, a central processing unit, works. It's quite good. It's only, I think it's less than 10 minutes long. So now we're going to switch gears and talk about computer networking concepts. And in our CSET program, the Computer Systems Engineering and Technology, the students become proficient with computer networking. So today, the internet allows one to connect to other computers anywhere on the earth through a vast computer network commonly referred to as the World Wide Web. This fact has changed how we work, play, learn, communicate. In fact, almost every aspect of human life has been touched by the internet. Computer networking is one of the most disruptive technologies to be implemented in the history of humanity. So here's a graphical representation showing just about everywhere in the world is connected. And if you're not connected, you're upset. It is instructive to examine how computer networking is achieved. There's a growing area in the computer support field. So early computer networking was proprietary. That is, only computers manufactured by the same company could communicate with each other. That changed when standards were adopted. So back in those days, DEC computers could talk to other DEC computers, IBM computers could talk to other IBMs, but they couldn't communicate across the different manufacturers. We already know that computers can take data in, that's input, and send data out, or what we call output, also known as I/O. To implement computer networking also requires some specialized communications interfaces and a few other networking devices. So here's this is kind of stolen from Cisco, computer networking concepts. So notice you see on the picture here, we have a switch in the middle, and these other devices starting at the top, a file client, a file server, a web server, an email client, and a web client are all connected to the switch. So every computer connected to a network is called a host or end device. Servers are computers that provide information to end devices on the network. For example, email servers, web servers are the file servers, as shown here. Clients are computers that send requests to the servers to retrieve information, such as a web page from a web server or an email from an email server. So again, in the middle of that network is a switch. So the two most important computer networking devices need to facilitate networking are a switch and a router. The end device typically comes with the required communications interfaces. To the average person, their home network doesn't require them to do much of anything. Once they've logged on to the network in their residence, they are all set because their particular end device's operating system, or OS, and that could be a computer, laptop, tablet, cell phone, and so forth, will facilitate their future connections to the network. You come home, you turn on your computer, and it gets connected automatically. Their network service provider, typically Comcast in this area, has supplied them with a combination of router switch, typically with a wireless access point. That is their connection point to the internet. If you need to log on to another network, at say school or work, the scenario is similar, except you need a username and password for your first logon. After that, the OS will facilitate your connection. Most networks use wireless connections at this point, that is using Wi-Fi. So here's a picture of a Comcast Wi-Fi 6E cable modem. So Wi-Fi 6E access point and one 2.5 gigabit per second Ethernet port, and three 1 gigabit per second Ethernet ports. That's what you get in the back of that cable modem. Here's a Cisco Wi-Fi 7 access point connected, to the ceiling, or mounted on the ceiling rather. So a Wi-Fi access point basically connects one to a LAN, a local area network, which will provide access to the internet through a router. A switch is a basic device needed to form a network, while the routers need to connect the network to other networks. Most of this is hidden from the user. However, there is a need for computer support technicians to configure, implement, install, and maintain computer networks for enterprises. The CSET program provides these skills to our students. So here's an overview of network components. So the picture we see on the right-hand side shows a LAN, kind of yellowish color. Shows an internetwork in the middle, kind of pinkish color, and then LANs, another LAN on the right-hand side. So these two LANs are connected by the internetwork. So a network can be as simple as a single cable connecting two computers, or as complex as a collection of networks that span the globe, or again, the World Wide Web. Network infrastructure contains three broad categories of network components: devices, those are what you see basically in the LANs, media, and services. The media connect the devices together. So if you take a look on each one of these LANs, you see a switch connected to devices, both the left and the right-hand side. Then in the middle, you see a different symbol. Those are routers. Those are devices. So the routers are the things that connect different networks together. And it looks like routers connect other routers together. And notice there's multiple connections, so it turns out there's redundancy built into the internetwork. So we call these topology diagrams. So it turns out physical topology and logical topology. The physical topology is physically where things are located and so forth. Notice it says server room, server racks in a certain room rather. That's on the left-hand side, and then the right-hand side, the same diagram is shown with just IP addresses on a target. And then you see the network, it's a 192.168.10.0 and a 192.168.100.0. Then there's, again, all the IP addresses for the devices on the network, whereas on the physical topology, we're just talking about where things are located. So there are things called LANs and WANs, these different types of networks. So a local area network, or a LAN, spans a small geographic area owned or operated by the individual or IT department. A wide area network, or WAN, spans a large geographical area, typically involving a telecommunications service provider. There's other types of networks. There's MANs, Metropolitan Area Network, wireless LANs, or WLANs, storage area network, SANs, plus there's many other types of networks at this point. Now, what you learn in the CSET program is that all operating systems have the ability to actually take a close look at the hardware of the machine. So in Windows, there's something called the command prompt. And if you get into the command prompt, and you could do a search on that for your computer, and it'll CMD, this command prompt, and it turns out that once you get in there, a screen comes up, and you can put in a command, and this command is ipconfigure/all. And what happens here is you bring up all the information about the IP addresses, the MAC addresses, and so forth, the DHCP servers. There's a whole host of information that tells you how your computer is communicating. Switches. Here's a picture of some switches. They will have numerous RJ45 ports, which are, computer networking cabling ports for some type of end device to connect that end device to a network. So here's just three different types of switches. The bottom one has the most ports. Routers. Routers will have network interfaces of various types. Might be Ethernet, again, like the switches, 5G, Wi-Fi, fiber optic, and so forth. All kinds of different. You see a bunch of antennas on these, so a lot of these are wireless routers. And the front of the router usually doesn't have too much other than a front panel. Most of the routers, it's made by Cisco. The work area of the router is in the back side of it. How do we talk to these types of devices? Well, again, the CSET program, one of the things we do is give you the skills to be able to take and talk to these devices, set them up and so forth, ask them questions, troubleshoot them, and so on and so forth. So Cisco switches and routers both have a type of operating system known as iOS, or Inter-Network Operating System. This allows one to talk to the device in several ways. When one configures a switch or a router, it is typically done to make it an integral part of a computer network. Typically, one uses a CLI, or command line interpreter mode, of talking to a Cisco networking device. So the Cisco iOS, it turns out its operating system As pointed out in this slide, all electronic devices require an operating system. Windows, Mac, and Linux for PCs and laptops, Apple iOS and Android for smartphones and tablets, Cisco iOS for network devices, that is switches, routers, wireless access points, firewalls, and so forth. So this kind of shows a graphical, the OS shell. The operating system shell is either a command line interface, a CLI, or a graphical user interface, a GUI, and enables a user to interface with applications. If you think about Windows, Windows is a graphical user interface. You point and click on icons, and you cause the computer to do things that way. With Cisco routers and switches, you have to use the command line interface. You have to type in commands. Inside that OS shell is an OS kernel. The OS kernel communicates directly with the hardware and manages how hardware resources are used to meet software requirements. Then finally, the most inner circle of this diagram is the hardware. That's the physical part of a computer, including underlying electronics. So, access methods. Three most common ways to access the iOS, the Cisco iOS that is, are the console port. That's an out-of-band serial port used primarily for management purposes, such as initial configuration of the router. That is, you have to plug in a special cable. Then there's a secure shell, SSH. That's an in-band method for remotely and securely establishing a CLI session over a network. So I remotely access the switch or router. User authentication, passwords and commands sent over the network are encrypted. As a best practice, use SSH instead of Telnet whenever possible. Telnet is not very secure. Telnet is an in-band interface, remotely establishing a CLI session through a virtual interface over a network. User authentication, passwords, and commands are sent over the network in plain text. Plain text, again, is not very secure. So this is an example of how we would take and configure, say, a host name, whether it be a switch or a router. So once the naming convention has been identified, next step is to apply the names to devices using the command line interface. The host name global configuration command is used to assign a name. So when you first turn on a switch, what happens is it boots itself up, and eventually on the screen you see switch, and then you type in enable. It changes the configuration that the switch is in. Notice there's a little caret symbol first, and then there's a hashtag symbol. Once you're in the hashtag symbol configuration, you can take and type in configure terminal. Once you do that, it comes back a switch configure hashtag. Then you type in host name. This is switch floor 1, and you type that in, and it turns out the switch will change from being switched to switch floor 1 as its name. This is the type of stuff that you learn in the Cisco courses in the CSET program. How about IP addressing? Turns out every end device on a network requires an IP configuration consisting of its IP address, something called a subnet mask, and a default gateway, which is optional for some devices. So how can we get in to do that? Well, we can go to network settings in our operating system under settings in Windows 10 or Windows 11, and turns out we can access and change these settings if we want. IP version 4 addresses are displayed in dotted decimal format consisting of 4 decimal numbers which go from 0 to 255, separated by decimal points or dots, and some examples are our favorite 192.168.1.10, or say 255.255.255.0, or maybe 192.168.1.1. And again, you learn how to do this in the CSET program. Interfacing and ports. Cisco iOS Layer 2 switches have physical ports for devices to connect. However, these ports do not support Layer 3 IP addresses. To remotely connect to and manage this Layer 2 switch, it must be configured with one or more switch virtual interfaces, or we call them VSIs. Each switch has a default VLAN 1 virtual switch interface. Note, a Layer 2 switch does not need an IP address to operate. The SVI IP address is only used to remotely manage the switch. manual IP address configuration to end devices. Here we can manually configure an IP address on a Windows host. So if it's got Windows 10 or 11, you open the control panel, Network Sharing Center, change adapter settings, and click on the adapter. So again, this slide tells you a little bit how you go about doing that, and hopefully in lab we will have a chance to play with that. How about this switch virtual interface? To configure an IP switch virtual interface, to remotely manage the switch, it must also be configured with an IP configuration. However, the switch does not have a physical Ethernet interface that can be configured. Instead, you must configure the VLAN 1 switch or switch virtual interface, SVI. So, how do we do it? It must be configured with an IP address, a subnet mask, and enabled using a no shutdown command. And again, notice there's a lot of commands that one has to learn. Interface addressing verification, the IP configuration on a Windows host is verified using the IP config command. I've mentioned that previously. For a router or a switch, we use the show IP interface brief privileged exec command, and that'll tell us what the IP addresses are of a SVI. The ping command, the last thing I'm going to talk about, or close to the last thing, is an end-to-end connectivity test. So the ping command can be used to test connectivity to another device on the network or a website on the internet. And we'll have some examples of that. So here's IP addressing, and IP addresses are more complex than just a 32-bit address. One portion of the 32-bit IP version 4 address identifies the network, and another portion identifies the host. So all the end devices on a particular network, local area network, would have the same network portion to their IP addresses, but the host portion would be different for each one. This one shows 192.168.10, where the host portion, which is again particular to a certain computer or end device on a network, has a number 10 in this particular example. And then the subnet mask, comparing the IP address and the subnet mask, the ones in the subnet mask identify the network portion while the zeros identify the host portion. So what we do is we AND together the IP address and the subnet mask, and that grabs for us the network portion or the network IP address. And I think that's my last slide.